Section 6.2 is on page 420. It talks about the pigeonhole principle. There's a diagram in the book on page 420. You could look it up, and the link explains what it is. It says, suppose that a flock of 20 pigeons flies into a set of 19 pigeonholes to roost. Because there are 20 pigeons and only 19 pigeonholes, at least one of these 19 pigeonholes must have 2 pigeons in it. Assuming that each one chose a unique pigeonhole, then the 19 will fill all 19 and the remaining one must go with another. Of course, if that's not the case, then you could have some empty pigeonholes and 3-4 pigeons in one, and so on and so forth. That's why it says at least. To see why this is true, note that if each pigeonhole has at most 1 pigeon in it, that's what I just explained. So this principle is called Pigeonhole Principle. It's extremely useful for what we're going to use. You could look it up in the diagram. You can see that on page 420 in the book. But we want those 2 theorems. Extremely important. Especially the first one we're going to apply a lot more. It says, if k positive integers and k plus 1 or more objects are placed into k boxes. So if we have k boxes, 10 boxes, and we want to place 11 objects in them, then at least 1 box will contain more than 1 object. So hopefully that makes sense. If I have 10 rooms and I have 13 students, well, the best I can do is fill in each classroom with 1 student. That will be 10 students to 10 rooms, and I have 3 students over. I have more students than rooms available. So there will be at least 3 classrooms that have more than 2 students, assuming I did the best scenario. And this is also very useful. We're not going to use it as much, not yet. If n objects are placed into k boxes, so n objects k boxes, then there's at least 1 box that contains, notice this is the greatest integer rounded up. So this is like when you say I need 8.3 gallons of milk. Well, you can't get 0.3, so you buy 4 gallons of milk or paint or something that you can buy a whole from. So you always round up pretty much. I'll apply that. I'll show you how to use this to figure this out and how could this be very useful. So I'm looking at problem number 2. This is on page 426. It says, show that if there are 30 students in a class, then at least 2 will have last names beginning with the same letter. All what you have to do in this is show me k, where k is like the number of boxes or slots. Well, if we really want the best case scenario, assuming that each student has an unique last name, then I could have 26 students with different last names, provided that did happen. And then 4 students must repeat. So that's at least 2. That's more than 2. So there it is. You could just say that I could have 26 unique last names because of there are 26 letters in the alphabet, and after that 4 must repeat, so that's at least 2. Now, if I look at number 4, a bowl contains 10 red bowls and 10 blue bowls. A woman selects bowls at random without looking at them. Okay, so we have 20 total. How many bowls must she select to be sure of having at least 3 bowls of the same color? So how many bowls must she choose so that she is guaranteed to have at least 3 bowls of the same color? So the best case scenario in part A. If she picked 2 red and 2 blue, you want 3, right? So after the best case, let's say she picked 1 red, 1 blue, or 2 red and 2 blue in any order. But the worst or the toughest case scenario would be she will pick 2, 4, and she will need 1 more to have them the same color. So she needs 5, at least 5. And part B, it's asking, how many balls must she select to be sure of having at least 3 blue balls? Well, you think of always the worst case scenario. That's possible. She could pick the 10 all red first, plus 3 blue. That will yield at least 3 balls. So at least, how many balls must she pick? I shouldn't say at least. How many balls must she pick? If she picks 13 balls, she's guaranteed to have at least 3, because she could have picked that before that, right? So with 13, you could have 3 or more, because you could pick, instead of all 10 red, you could have had, like 8 red and 2 blue already. So 13 is the number that guarantees that this is going to happen. And that's really what you want. You want to ensure that you touch on all of these different objects. Number 6, there are 6 professors teaching introductory discrete mathematics. So we have 6 professors. The same final exam is given by all 6 professors. This is like common finals. They do this a lot. So we're given the 6 exams by all professors. If the lowest possible score on the exam is 0 and the highest possible score is 100, so that's 101 possibles. How many students must there be to guarantee that there are 2 students with the same professor who earn the same final score? Well, here we really have to look at 101. So if you take 6 times 101, that's 606, assuming that each professor in their class, somebody gets a 0, somebody gets a 1, a 2, a 3, a 4, a 5, a 6, a 7, all the way to 100. Second professor, 0 to 100. So the way this works against you, if that did happen, every professor had students scoring from 0 all the way to 101. That's 606 different scores, because they're taking the same scores, the same score but with different teachers. So each teacher has a student that scored 1 of each grade possible, assuming halves and quarters are not given. So we need 607 students to take the test. And we are guaranteed that, worst case scenario that's working against you, 606 would be taking the exam and scoring 0 to 100 in each teacher, but the extra student, no matter which professor they're taking, they must repeat now that you took all the possible values or outcomes. And for programming, this is a must. Interesting problem. I didn't really touch on a lot of those because I wanted to digest the actual application before we go to proofs and variables. Let D be a positive integer. So D could be any positive integer. Show that among any group of D plus 1, not necessarily consecutive integers, there are 2 with exactly the same remainder. Well, let's see. If we take D, D positive integer. Let D be some number. 4, 5, 6, 7. If I divide by D, the remainder is a 0, 1, 2, 3, all the way to d minus 1, true? If the remainder is d, it will divide into d one more time, and you'll get a remainder of 1. So the possibles are those. Show that among any group of d plus 1, if I take d plus 1, these are the possibles right there. Doesn't that mean from d minus 1 to d plus 1, that is 2, at least 2 would be 2, assuming that the case did happen where each number gave a 0, 1, 2, 3, 4. So this would be 2 extra, meaning repeats, and that's what they're talking about. Among there are 2 at least with the same remainder. 2 will repeat for sure. Make sense? Number 16. So this show, you're not proving, you could say that in words. You could write down what I'm saying in words. You could describe it, you could say, this is all the possible remainders. So d plus 1 will have whatever this is plus 2 extra remainders. So on a test, that's what you could say. You could give that the 2 extra or d plus 1 and explain that. For the previous problem, you could give the 607 and explain that, 606 will be unique solutions or unique scores, and the 1 extra must fall into one of the professors, and that's the repeat. Number 16, I'm sorry. 16. Show that if 7 integers are selected from the first 10 positive numbers, so we're talking about 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Show that if 7 integers are selected from the first 10 positive numbers, there must be at least 2 pairs to have a sum of 11. Well, let's figure this out. How could you get a sum of 11? 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. The best you could do to avoid a sum of 11 is to choose either those or those. So you could have best case scenario that's working against you, you choose 5 numbers. So if you choose 5, those could be best case scenario unique. Well, how many are you choosing? 7. If you choose the red, by choosing any of the green, 2 of them, you're guaranteed to get 2 sets that add up to 7. How about B? Is the conclusion in part A true if 6 integers are selected rather than 7? Well, if you select 6, the best case scenario, 1, 2, 3, 4, 5, that's the worst case scenario against you. If you choose one more, any number, say 9, then you will only get 1. So no, that wouldn't be the case. Only one group is guaranteed to have a sum of 11. Now you could have 11 if this doesn't happen. We're going to assume the worst case scenario every time because we want a guarantee of these things happening. How about 18? How many numbers must be selected from the set to guarantee that at least one pair, just one pair, add up to 16? How many 16s are there? 1 and 15 is 16. 3 and 13 is 16. 5 and 11 is 16. 7 and 9 are 16. So if I had the worst of luck and I chose either the red or the green, then 4 distinct. So one more. So by picking 5 numbers will guarantee at least sums that add up to 11. Add up to 16. You know what I mean. Now, why do we say at least? Because you could choose 1, 3, 13, and 5. You could do that before that. But worst case scenario, pick 5 and you're guaranteed that's going to happen. And that's why the word at least. That could happen before. 20. Suppose there are 9 students. 9 students in a discrete math class at a small college. Show that the class must have at least 5 male or at least 5 females. Part A. Let's assume it doesn't happen. So, if it doesn't happen, at least 5 males, that means we have 4 or fewer males, right? And 4 or fewer females. But that's 8 students. That's a contradiction. Therefore, our contradiction is false, and there must be at least 5 of males or females, right? One of them. How about B? Show that the class must have at least 3 male students or at least 7 female students. So we're going to do the same. If not, then at least 3 males, we're going to have 2 males and 6 females, but that's 8 students. That's a contradiction. Therefore, there must be at least 3 males or 7 females. All right. 34. Show that if there are 100 million wage earners in the United States, 100 million wage earners who earn less than $1 million, but at least a penny. Then there are 2 who earn exactly the same amount of money to the penny last year. Well, if you really think about it, at least a penny. So that's running 0.01 penny all the way, and less than $1 million, $999,999. Less than $1 million and 99 cents. Well, 100 million is definitely more than $1 million. There's 1 million distinct salaries or wage earners, whatever, and we have 100 million. So that's definitely more. By the Pigeonhole Principle, K is bigger than, it was K, right? Just recall really quick. K is $1 million, but we have 100 million, right? So that's more. For sure, not 1. A lot more I'm gonna repeat. So more than 1. Which is what they want. At least 2. Could be 2, it's gonna be way more than 2 even. right? The best you could have, so the worst case scenario and we always assume the worst case scenario, you get 1 million people that each one earn different values. And then you get 999,000 people that earn one of the same amounts, say $1. $1. So if you look at $1, let's say the worst case scenario, you have 1 million of those and 999,000 earning $1, right? So the extra person after that is either gonna repeat one of the other values, and that's where the at least 2 come from. But we have 100 million, it's not that close. And that's pretty much it for this section.